Hello and welcome back. So now we're going to continue talking about dominoes. In the first part we describe the game and we calculate the probabilities of specific outcomes, for example, the probability of seeing 1/6 and probability of certain events that have to do with a single tile and two tiles. And we also did some simple examples. For example, we did probability of the second is a match given the first one was double or not double. And what we want to do now is to do a single longer example. And as we said, it's optional, so don't have to watch if you don't want. Okay, so so first of all, arbitrary first tile. So what we've done so far, as we said, is we calculate the probability that the second tile is a match given when we were told what the first tile was. So we saw what happens if the first tile was a double, for example 6/6. We calculated the probability of a match, and we saw the probability of a match when the first tile was non-double, like 1/3. But a more natural question, and it's also closer to the game, is to say that we're drawing one tile and then another tile, and without replacement, of course. And then we ask just what is the probability that the second one matches the first. So for example, the first one could have been 1/3, which is not a double, and the second one is 5/1, it matches in a 1, it's good. Or the first one was 4/4, which is double, second one is 2/6, there's no match. Okay, so in other words, we're not conditioning on the first tile. We're not saying the first one was a double or not double. We're just saying we're picking one tile, then another one. What's the probability the second will match the first? Okay. Now, of course, as we always do with dominoes, selection without replacement. We select one domino, we place it, and then select another one. And if you remember from when we discussed selection without replacement, then an equivalent way of calculating this, instead of saying pick the first then the second, is just to say that we're drawing two tiles without replacement, and you ask what is the probability that they share a common number, like here. So we draw the first tile, and we draw a second one, and we are interested in the probability they share a common number, like here 1, and equivalently we could just say we're drawing two tiles. Let's wait until we draw both of them. We don't care which order, we just ask what is the probability that they share a common number. Okay, so so to calculate it, as usual, we need to calculate the sample space. We need to observe that in this case it's uniform, and then everything will be easy. Okay, so what is the sample space? It's the collection now of all tile pairs. So for example, 0, 0, and 0, 1, or 0, 0, and 2, 6, and there are many more, 6, 5, 6, 6, many more tiles. Now notice that I'm calling it omega because that's our generic name for the sample space, but this now is not the same omega as in the first part. The first part was just the collection of all tiles, which was 28. Now it's a collection of all pairs of tiles, which will have many more elements. Okay, and now we are interested in the event that that the two tiles that we pick are matching. So M, our event of matching, will be the collection of all matching tile pairs. For example, 0, 0, and 0, 1, they match in 0. 1, 3, and 5, 1, they match in 1. These two match in 6, and so on. Okay. Now notice that our space is equiprobable. The probability that we'll pick this pair is the same as the probability we'll pick this one, and so on. So by uniformity, the probability that we'll get a matching pair is just the number of matching pairs divided by the total number of pairs. Okay, so the size of this set of matching pairs divided by the size of the sample space, the collection of all possible pairs. And so if we calculate these two, we'll have our answer. Now, of course, the easier one to calculate is the size of omega, the number of all tile pairs. Okay, and so notice that a pair is just 2 tiles out of 28. So we have 28 tiles, and we pick 2 of them. Each one is a pair. So how many ways can we pick 2 out of 28 tiles? That's going to be the size of our sample space, which is 28 choose 2. Okay, and we're not going to calculate it because as usual, we'll have lots of cancellations, so we'll just leave it at that. Okay, and the only thing that we have left to do is calculate the size of M, namely how many of these 28 choose 2 pairs, how many of them are matching pairs. Okay, so that's what we're going to next. Okay, so to do that, we're going to observe a simple structure for M, the size of the collection of all matching pairs. So M is the collection of all matching tile pairs. and consists of 0001, 1315, and so on. Okay, so what we're going to do is we're going to partition this set M by the number that the tiles share. So here they share 0, here they share 1, here they share 6, and we're going to partition it based on that. So we're going to define M0 to be the matching pairs that share 0. Okay, for example, 0001 shares 0, 0204, 0205, there are many more. Okay. And similarly, we're going to find M1, share 1, and so on, up to M6, which is the collection of all matching pairs that share 6, and that consists of 5, 6, 6, 6, share 6, 1, 6, 3, 6, again, share 6, and so on, and many more. Okay. And now, an important observation is that these 7 sets, M0 up to M6, they partition M. What do we mean by that? We mean that together they cover M, namely, if you take the union, it's going to be M. Each one here is a subset of M, but if you take the union, you'll get all of M back. So that's one thing, they cover M. And the second property they have is that they're disjoint. Namely, if you take M1 and M6, for example, here, they do not intersect. There is no pair that is both here and here. Okay, for line not equal to J. To observe the first property, that they cover M, just observe that if you take any pair in M, for example, 1, 3, and 5, 1, they share 1, therefore they will belong to M1. If you take 0, 0, and 0, 1, they share 0, they'll belong to M0, like this. Take 6, 5, and 6, 6, they share 6, they'll belong to M6. So every pair that you take here will belong to one of the sets here, and therefore when you take the union of the sets, you'll get all of M. To see why these two sets are disjoint, for example, why is M0 disjoint from M6, assume that you have an element which is in M1. We're going to show that it's not in any other M. If we show that, that would mean that the sets are disjoint, because we're saying that if it's one of them, it cannot be in any other. So take, for example, 1, 3, and 1, 5. They belong to M1 because they share 1. We want to show that they're not, this pair is not in any other M2, M3, and so on. So first observe that because they are in M1, then both tiles have a 1, because they're in M1, and so let's assume that the 1 appears on top. Now let's consider the bottom. Because these are two different tiles, and they're the same here, the bottom must be different. We cannot have 1, 3, and 1, 3, because it would be a single tile, not a pair of tiles. So these bottoms must be different. Okay, and because the bottoms must be different, they cannot be in any other MJ, because for example, they cannot be in M3 because this one has 3, but this is different, so this tile cannot contain also 3, so they're not in M3. Cannot be in M5 because this has 5, but therefore this one is different, so it's not 5, so it cannot be in M5, and also they cannot be in M4 because actually none of them have M4. So this means that, for example, this pair is in M1, and therefore it is not in M2, M3, it is not in Mi for any I which is not equal to 1. Okay, and that shows us that the MIs are disjoint, right? Because if you take any element and belongs to M1, for example, it cannot belong to any other MJ. Right. So what we have is that the MI is partition M, the union is M, and they're disjoint, and this will be very helpful in finding the size of M. Yes, that's what we're going to do next, calculate the size of M. So M, remember, is the collection of matching pairs, and MI is collection of matching pairs that share I, they have I in common, and we just saw that the MIs partition M, okay, and that means that they cover M, namely the union M0 up to M6, the union of those 7 sets is M, and we also saw that they're disjoint, so it's that M each, they do not intersect. So in other words, this is a disjoint union, which if you remember back when we talked about counting, we denoted by this MasterCard, two disjoint circles. Okay, so they're disjoint. And the most important result we had then was the additive rule, that if you have a disjoint union, if you have a union of disjoint set, then the size of the union is the sum of the sizes of the sets. So the size, therefore the size of M is just the sum of the sizes of these 7 sets. Okay, M0 up to M6. So all we need to do is just calculate the sizes, and we'll be just add them, and we'll be almost done. Okay, so just need the sizes of the MIs. So let's look at M0, for example. So what is M0? It's a collection of all pairs that share 0, that have 0, both of them. Okay, so what we need, so M0 consists of all pairs that are taken from these that have a 0, namely they're taken from these 7 tiles. Okay, for example, 0, 0, and 0, 4. Take this one and this one. It's a pair that shares 0. Take 0, 5 and 0, 3. They'll share 0. So M0 is just a collection of all pairs, all 2 tiles selected from these 7. So how many such pairs are there? Well, we have 7 tiles with a 0. We need to choose 2, so it's just 7 choose 2. Okay, so this is M0. Maybe M1 will be more difficult. Let's see. So M1 consists of any 2 pairs from the tiles that have a 1, 0, 1, 1, 1, 1, 2, up to 1, 6. Okay, so if you take any 2 tiles from this 7, for example, 1, 3, and 1, 5, well, they share a 1. So any pair that you take from here will share 1. No other pair will share 1. So how many such pairs? How many M1? Again, we need to choose 2 tiles out of the 7. 7 choose 2. Okay, so life is good. The size of M is the sum of 7 sets. Each of them has this size. So the number of matching pairs is just going to be 7 times the size of each of those sets. So it's 7 times 7 choose 2. Again, we can calculate, but we won't because we want to just divide. So let's just remember. So the size of M, this number of matching pairs, is 7 times 7 choose 2. Okay, so now we can just put things together. So the probability that the second tile matches the first is the probability that the first 2 are a matching pair. And so because all matching pairs, all pairs have the same probability, so it's just going to be the number of matching pairs divided by the number of total pairs. Okay, and we just saw that the number of matching pairs is 7 times 7 choose 2. And beforehand we said the total number of pairs is 28 choose 2 because we have 28 dominoes. We just need to choose 2. And so the probability that the second tile matches the first is just this ratio, which is 7 times 7 choose 2 divided by 28 choose 2. And now we'll see why we didn't calculate these numbers. So we just open them up. So we have 7 times 6 over 2 divided by 28 times 27 over 2. Okay, and we have some nice cancellations. The 2's cancel. Oh, that's not it. The 7 cancel with the 28. Gives us 1 over 4. Okay, now the 6 will cancel with the 4. Will give us 2. And with the 27 will give us 9. So 2 times 9. So on top we just have 7. The bottom we have 18. Okay, which is 0.389. Okay, so actually maybe it didn't turn out to be so difficult. We're done. So we calculated the probability that the second matches the first, and we got it to be 0.389, and hopefully it was not that difficult. All right, so we just now want to say a couple of things about that. So first, remember that in the first part, we saw that if the first tile was a double, then the probability of a match was roughly 0.222, a little less than a quarter, if you remember. If it was non-double, then the probability of a match was twice that, namely 0.444. Now we're calculating the probability the second is a match, and we don't know if the first one is a double or not double. So it makes sense it will be somewhere in between, because some probability it's a double, some probability is not a double, so it should be kind of like some average. And indeed, when you look at it, 0.389 falls between those two, so I think we're a little safer. Okay, so that this a little more, have a little confidence that this is probably correct, and it is. Okay, so that's one thing. And also I want to say, why did we say that this is optional? Because the way we calculated was a little macho man way of doing it. We calculated this factorial, and this factorial was a little complicated. Later on, when we're going to talk about conditional probabilities, we're going to see that in fact, this number can be found even by a sleeping baby. Okay, so with that, let's summarize. So we talked about dominoes, we described the game, we calculate probabilities of specific outcomes, namely of observing a single tile, and of the probability of events, calculate probability of events for when we select a single tile, and we can select 2 tiles, and we did it in 2 parts. The first one had some simple example, and the second one had a longer example, although maybe not really much more complicated. And with that, we are done with this, and we made it optional. And next time, we're going to talk about card probabilities. See you then.